All right, welcome back, friends. Here we have problem number 12 of the MIT Integration Bee. We have the integral of the hyperbolic tangent squared of x dx. So this is kind of a grisly one um, because I don't think anybody really has memorized the hyperbolic tangent functions and their squares and the integrals of those functions. But I think as any mathematician would tell you, it's good to kind of create a relationship between functions that you know and functions that you don't know. So let's say the integral of a function that we know, or I don't know, let's start with the Pythagorean identities of tangent, or better yet, tangent squared. So we don't know hyperbolic tangent. We know that um, tangent squared, let me just not be on my eraser. We know tangent squared plus 1 is equal to secant squared x. So if we look it up and we look up our hyperbolic trig identities, we'll notice that hyperbolic tangent squared x plus hyperbolic secant squared x is equal to 1. Or, in other words, hyperbolic tangent squared is equal to 1 minus secant, hyperbolic secant squared of x, which is the opposite of what we had here. So we can rewrite our equation as this, which is 1. I'm actually going to just go ahead and split it up now. 1 minus the integral of secant, hyperbolic secant squared of x dx. So we know that the integral of secant squared, secant squared x dx, that's going to be tangent x plus c. And we know that because we know that the derivative of tangent is secant squared, so the antiderivative of secant squared must be tangent, right? So the integral of secant squared is tangent. And we know that, these two functions are probably opposites, right? We know that hyperbolic sine and hyperbolic cosine, they derive and are integrals of each other, but the hyperbolic versions of those functions are both positive always. Well, not always, but most of the time for, kind of an average. We can assume that they're positive, like the derivative is positive, but the geometric identities, so just regular sine and regular cosine, they keep flip-flopping, right? So the derivative of sine is cosine, but the derivative of cosine is negative sine, right? It has this negative 1 value, which does not appear in the hyperbolic sine or hyperbolic cosines, right? So I think it's reasonable to assume, based on other things that we've learned about these functions, we don't have to look it up. If we look it up, we'll find that it's true, but if we don't look it up, we don't have to, because we can make a reasonable assumption that because this is true, we can conjecture that this is true, then the negative of the hyperbolic version, which is down here, this just means that's just x, we can say that the negative version in the hyperbolic world is actually going to be equal to the positive hyperbolic tangent function. If we look this up, it's actually true that our integral is actually going to be equal to x plus hyperbolic tangent of x plus c. And again, in mathematics, this is a very important skill to learn, is how to make a reasonable conjecture based on things you know about other related functions. So here what we said is we said that tangent and hyperbolic tangent seem to be opposites of each other, right? So tangent plus 1 is secant squared, but hyperbolic tangent, so if we add plus 1 over here and move that over there, if we add, so hyperbolic tangent squared plus 1 is negative secant squared. We also then can reason from that if we take the integral of secant squared, it's going to be tangent x. If we take the integral of hyperbolic secant squared, or the negative integral of hyperbolic secant squared, it will still be positive x, right? If we took the integral, the positive integral of secant, hyperbolic secant squared of x, we would then reason that it would be negative tangent, because they're opposites. Sweet. All right. Good conjecture.